didn't see you standing there. Everyone has been asking all about atoms, and I don't even remember now how the topic came up. We were talking about something. Anyways, unfortunately, I have some bad news. We don't have time to talk about atoms in the course of a normal school day. I wish we could just show up at school and I could say to you guys, okay, what do you want to learn today? And we could just go learn about it. But unfortunately, we can't. So, sorry, we can't learn about atoms. But we can learn about them through the miracle of the internet. I mean, 20 years ago that was impossible, but now you guys, I can send you a video all about atoms. So, we're going to talk about atoms, we're going to talk about what they are, we're going to try to think about what they might look like. I might even show you a picture of an atom, and then we'll do a little bit of experiment. So, if you're ready to learn about atoms, keep watching. So, everyone say hi to Grizzly. Hi, Grizzly. Hi, Grizzly. Hi, Grizzly. Yeah. We're going to talk about atoms, and up here on the table I've put 1, 2, 3, 4 things that are probably about as dissimilar as you could possibly get. I've got an apple. I've got my dog, Grizzly. He really wants the treat. I've got a bottle of olive oil, great for cooking, and a speed cube. And the miracle, really, the amazing thing about atoms is that all 4 of these things, they're all made of atoms. The apple's made of atoms, Grizzly's made of atoms, Grizzly's treat is made of atoms, the olive oil, everything's made of, I'm made of atoms, you're made of atoms. It's all just atoms. And that should blow your mind. It blows my mind. How can all of this stuff that's so different be made of like the same thing? How does that happen? If you want to make a cake or you want to make a nice steak dinner, you can't use the same ingredients. You have to use totally different stuff. But here we are, and we're all made of the same things. We're all made of atoms. Grizzly, you've been a very good boy. You ready? You ready? Okay. Oh, well done, mate. Good job, buddy. Okay, time to come down now. Time to come down. Yeah, it's not safe for doggies on counters. Please don't put your doggie on the counter. Okay. There he goes. Alright, so, where was I? I lost my train of thought. I usually do that when I pick up my dog. Oh yeah, so, anyways, everything's made of atoms, but these things are all different. So, maybe we can get some idea of what makes them different if we can try to see an atom. So, let's see if we can find an atom. Okay, let's see if we can find an atom. I know the atoms are small, so maybe if I get this as small as I can make it, we can find an atom. I mean, that makes sense, right? In fact, atoms have been known about for thousands of years. You might have heard of the ancient Greeks. The ancient Greeks knew that there must be a concept of an atom. There must be something that is the smallest thing. If we keep having this apple, we can get to the smallest portion of apple. So let's do it. Let's find the smallest portion of apple. Don't use knives at home unless being supervised by a parent, and always be safe when you use a knife. Okay, so I'm going to just have this apple. My 11th cut, I can't really even separate. Let's try that again. 11, there we go. Okay, I'll try for 12. I'll try for 12, here we go. Go this way. Yes! Got it. Okay, here it is. You can see it on the blade here, we'll just use that as a bit of a display. Okay, there it is. There's our 12th cut of apple. Yep, I might put it down here. Now, if I wanted to look at this and think, oh, surely this is small enough to find atoms. Well, I'm going to be sorely mistaken. I'm going to draw a number for you. I'm going to show you just how many atoms are in this tiny piece of apple. Check this out. Grab a trusty piece of chalk. Hang on. I keep all my chalk in my own secret chalk drawer. Chalk. Inside that tiny little 12th half of an atom, you have about of an apple. You have about this many atoms. There's keep going. Hang on. Yeah, keep going. Yeah. about that many atoms. So, unfortunately, I think you can tell pretty quickly there's no way I could ever slice this down to such a small size that I could even hope to see an atom. It is impossible. It's impossible to see an atom with just your eyeball. But we've designed machines that can take pictures of atoms.
Okay, before I show you a photo of the atom, I just thought I'd show you a little model of the atom. This is what everyone's used to seeing in their books, or when you go on YouTube or Wikipedia and you see, hey, what does an atom look like? You see something like this. But this isn't what an atom looks like. This is just a drawing of an atom. It's a model. In fact, this one here is 3 atoms stuck together. And these 3 particular atoms, when stuck together, they make water. Maybe you've heard that water is H2O. Well, you have 2 hydrogen atoms, 1 hydrogen here, 1 hydrogen here, and it's stuck onto an O atom, an oxygen atom. When you stick 2 hydrogen and 1 oxygen, you get something called water. Isn't that amazing? There's another one over here. This is carbon. And, you know, they look like a pretty normal size. But if I were to zoom in on this display here, kind of zoom down like this, I can see that there's actually atoms that are even smaller than a water atom. There's the hydrogen atom or the helium atom. And then if I wanted to see how big those little bits were, I can zoom even further. Whoa, look at this. Here's the electron. That's the little yellow guy that's flying around the outside. And even further, I get to these bits here, the proton and the neutron. That's what makes up the center of the atom. So I'll zoom back out. And we'll just look at these atoms. So let's look at the helium, for example. It's got this center here, the protons and the neutrons bound together, and then these electrons kind of flying around. Okay, so you've seen what a model of an atom looks like. This is an actual photograph of an atom. Now, to call it a photograph is probably not quite true, because when you look at the technical way that this was captured, it wasn't really a photograph per se. But anyways, just for all intents and purposes, we'll call this a photograph of an atom. And you can see, amazingly enough, it actually looks like the model. You've got this center part, the nucleus, you've got this cloudy haze around there with the electron flying around. And the crazy thing about atoms is that, in fact, there's really not much there. Atoms are mostly space. I mean, there's a ton of space between the center of the atom and the outside edge of the atom, which really makes you think, like, if we're all made of atoms, and everything's made of atoms, and atoms are really just a lot of emptiness with a few little particles floating around, why can't I just, like, walk through a wall? Strange, isn't it?
So, let's do an experiment. We can prove that atoms exist in our kitchen. Okay, so we said that no matter what we do with this apple, we could never slice it thin enough to find an atom. But it doesn't mean we can't prove that atoms don't exist. In fact, we can prove they do exist with a really simple experiment at home. Now, this experiment has a fancy name. It's a demonstration of something called Brownian motion. Because a physics professor, a physicist, whose last name is Brown, described this kind of motion. And it was made famous by someone named Albert Einstein, who took his ideas and realized, hang on a second, this actually proves the existence of atoms. And we can do it right in our kitchen, which is really cool. So, let's look at the experiment. I've got normal tap water here, normal temperature, nothing special. In the middle, I have some red food coloring. And on the right, I've got some near boiling water. Now, if you use boiling water at home, you have to use it with mom or dad around, or a parent, because you can burn yourself. So, I'm going to pour the food coloring into this water first. And we're just going to watch what happens. I'm going to talk a little bit about what you're seeing. Are you ready? Okay, here we go. So, it's starting to sink down. We're going to give that a minute. Let's come over here to the hot water, the boiling water. And we'll do the same exact thing. Let's watch what happens. Oops. Oh, look at that. Look at that. That's so cool. Okay, so the boiling water is already almost instantly red, covered up in red. And look over here at this glass. Look at that. There's still plenty of patches where it hasn't dissipated yet. What's going on? You know? Why would the boiling water fill up with the red food coloring first? Oh, the secret. secret to this experiment is atoms. See, both the water here and the water here have atoms, almost the same exact amount. But the atoms in here aren't hot, so they're not jiggling around very much. But the atoms in here are really hot, so they jiggle, they move around. And that movement pushes the food coloring all around in the water, dissipates it out. So what's jiggling? Well, it's the atoms. The atoms are jiggling. So if there's no such thing as atoms, this experiment wouldn't work. We wouldn't have this result of the fluid being swirled around into the water the way it did. So a really simple experiment you can do at home that proves, hey, there must be these things called atoms, because without them, there'd be nothing to spread the food coloring around.